So, okay, so next week is the deadline for you to submit your proposals for term projects. So I still have received only one proposal so far, so you have one more week to figure it out. Keep in mind that I have to give you approval. So if I don't like your project, you have to find another one within the deadline, so better get going on that. Okay, so last time I had a question from you about what happens to the expansion and its rate of change when we're dealing with congruences in flat space. And you provided the answer, but I wasn't wise enough to recognize it at the time. So I'll answer your question with your answer. But I want to give a more a fuller discussion of all of this, because there are some interesting aspects to all of that I want to emphasize. So we're still talking about congruences of time-like geodesics. And so we've introduced all the formalism for this. We've introduced the decomposition of the velocity gradient field in terms of expansion, shear, and rotation. We've done all of these things. We looked at Ray-Chowdhury's equation. We derived the focusing theorem under the the specific conditions that the theorem holds. And what I would like to do now is to consider a flat space example so that we can get some familiarity with all of this and answer the question that you asked last time. So let's do an example of a diverging congruence in flat space. So let me draw it first, and then I'll describe it. Well, let me describe it mathematically first, and then I'll draw it so you see what it looks like. So I'm going to be working in spherical coordinates because it's going to be convenient for what we're doing here. So the metric of flat space in spherical coordinates is minus dt squared plus dr squared plus r squared d theta squared plus sine squared theta d phi squared. So I'm using tr, theta, and phi as coordinates. And what I want to consider here is the family of time-like geodesics. And I'll just tell you what they are. So T is going to be some constant, capital T, plus the parameter along the congruence, which I'm calling lambda. And lambda is not going to be quite proper time. It's going to be a constant times proper time. R is going to be a parameter v, which is a velocity parameter, times the lambda running parameter. So v is a constant. And theta is going to be a constant on the congruence. And phi is going to be a constant. But the constant can vary. So basically what I want to do is to launch a whole bunch of geodesics at all angles. And what I'm forming then is a cone of geodesics. And they're all moving with speed v relative to the reference frame. So the picture is something like this. We have, well, I'll draw it in 2 and 3D first. So we have the time direction running upwards, and I'm suppressing one of the spatial directions, and this whole family here, where I vary t and I vary these constants. Well, I think you'll see right away that it gives me just a family of time-like geodesics, time-like straight lines, of course, all moving on this cylinder. So this is t equals capital T, and I have, if I pick my two angles, I have one line moving this way, I have another line moving this way, and basically they move all around the cone like this. The cone, of course, is really three-dimensional, not two-dimensional. So I'm launching straight curves in all possible directions, and they all move with constant speed v on that cone. And that's one cone, but I can launch a cone at any value of t. So I have the cone here, I have the cone below, I have a cone below, I have a cone above. So I have a whole sequence of cones like this, and the whole thing forms a congruence. And I have three parameters to characterize, to label each geodesic within my congruence. So maybe to make the notation a bit clearer, I should say that theta, theta and phi are constants, and each geodesic is labeled by t theta naught phi naught, and lambda is an affine parameter on each geodesic. We're going to see in just a moment that this is not proper time. So let me just draw another picture so that we can see this a little bit better. So here I'm going to suppress the 2 dimensions. So I'm going to have time running upwards like this. I'm going to have x running sideways. And what I want to draw, so, with 1 dimension suppressed, my 3-dimensional network of geodesics was looking like a cone. Here, my cone is going to be, is going to be looking like a cylinder, like a triangle, like a wedge, like this. So it's really rotating around. So I have this, revolving around, but with 1 dimension suppressed, I have this wedge. So this is the wedge that's launched at t equals 1. This would be the wedge launched at t equals 2. This would be the wedge that's launched at t equals 0. So basically, for each value of t, I have a cone like this. So I'm launching those geodesics at all instants of time. So I'm really basically forming a congruence of time-like geodesics everywhere in space-time. Now, each of those points over here are places where geodesics are crossing, right? They all merge there. If you look at them backwards in time, they all emanate from those points if you look forward in time. So those are singular points on the congruence, so I'm going to be excluding those points. But apart from those crossing points, everywhere else, I have a bunch of non-intersecting geodesics, and I have a full congruence that fills all of 3-dimensional space, except for that axis over here, which is everywhere singular. So we're excluding the axis, we're excluding the singular points, and other than that, we have a perfectly well-defined congruence. So we're excluding the crossing points on the axis, which is a singularity of the congruence. Okay, so that's the system I want to study. So basically a whole bunch of straight lines, but they're diverging straight lines. And well, basically I can answer the question, I can answer the question that was asked. And the question that was asked is, well, how do we reconcile the focusing theorem with the behavior we would expect in flat space-time? And I think we were, and I know I was a little bit confused about the behavior that I expected in curved space-time, in flat space-time. And what we can use this example for is to basically, well, tell us what the proper behavior in flat space-time is when we're dealing with a bunch of diverging geodesics like that. So, so in flat space-time, and here I'm talking about fairly generic things, we know that we can have geodesics that are, deviating from one another by a vector xc. So that's something we talked about in the context of, well, the geodesic deviation equation and then this discussion of congruence. We know that the rate of change of xc, even in flat space, if you're talking about diverging geodesics, we know that this is not necessarily 0. If they start parallel, then the relative velocity between geodesics is going to be 0. But if they don't start parallel, then the relative velocity between geodesics is going to be a constant. And that's the situation here, because that velocity parameter over here is constant. So all those curves are propagating outward with a constant velocity, so that the relative velocity between them is going to be a constant. But what we know from the geodesic deviation equation is that the relative acceleration in flat space has to be 0. So that we understand. Now, when we talk about the expansion is really, roughly speaking, the rate of change on, I'll call it dd lambda, of the cross-sectional volume, which is measured by xc cubed, right? So it's nonlinear in xc, and that's the point I was missing last time, and that's the point you recognized last time, which means that it's 3 times xc dot over xc. This is constant, but this is changing, right? So when we calculate the rate of change of that, we get something that vanishes, but we get an extra term that is pretty important. So this vanishes, but this is something that's non-zero. And in fact, it's something that's guaranteed to give us a minus sign and a deceleration for expansion. So the point is that this behavior over here, which we know will happen in flat space-time, gives rise automatically to a congruence that's going to be decelerating in agreement with the focusing theorem. And in flat space-time, and we're going to see, I'm going to work through the details of that. In flat space-time, we're going to see that this is generated basically by, well, partly the terms on the right-hand side of Ray-Chowdhury's equation. So we're going to see that this behavior is compatible, it has to be, with Ray-Chowdhury's equation in the absence of a Ricci term on the right-hand side, and even in the absence of a rotation tensor, which in this case vanishes. So is that clear now? Yeah. So it was a simple point. I just failed to see it last time, even though you were pointing in that direction, but I was too tired to recognize, or too dumb, or something. So, but that's the idea. So even though we have no relative acceleration between geodesics, that doesn't mean that this quantity is 0, because this quantity is nonlinear in xc and measures a different thing. So even with no acceleration between geodesics, we still have a deceleration of the expansion parameter. Okay, so let me flesh this out a little bit. And what I'm going to do is to use this as an example to illustrate how the formalism works. And what I'll do on top of that is to take a limit where my velocity parameter tends to the speed of light. So we're going to take a light-like limit to that congruence and see what happens. And that's going to be my segue into the null case. We've treated the time-like case in the previous lecture. In this lecture, I want to treat the null case, and we're going to see that there are all sorts of interesting subtleties that arise in the null case, and we're going to see see them emerging from this calculation. Okay. Well, what I want to do is to start from this description of the congruence, and I'm going to work out the velocity vector, and then I'm going to work out the velocity gradient and everything that follows from all that. Okay, so the tangent vector to the congruence, tangent vector field, because we have a congruence at every point in space-time, well, u alpha, so I still call it u alpha, and in this case, it's going to be given by the derivative of the coordinates with respect to the adopted parameter, which is lambda, and this can be worked out easily. We just take derivatives, but everything is linear in lambda, so it's pretty simple. So the time component is 1, the r component is v, and the 0 and the angular component are 0. So that's a very simple velocity vector, but one thing you'll recognize here is that it's not normalized. So the inner product of u with itself is going to be minus 1 minus v squared. So it's 1 over the usual gamma factor squared. And I could have renormalized everything. I could have factored, I could have factorize this term over here to make everything normalized, I could have chosen tau as a parameter, but I just decided to keep it unnormalized like this in order to make the limit to the null case well defined. If I had adopted tau as a parameter, that limit would have been singular, and I would not have been able to take the light limit. So for the purpose of the discussion that will come out later, I'll just accept that my tangent vector field is not normalized. That doesn't change very much. All the stuff that we did last time is just that we need to adapt it a little bit to account for the non-zero normalization. So this is non-zero. This is non-zero. So, but that means that lambda is not proper time, but lambda is a constant times proper time, so it's still within the class of affine parameters. So that that velocity vector satisfies the geodesic equation in the usual form. Okay. For later purposes, or for the purpose of doing the next calculation, I'm going to lower the index on the velocity vector. And that's pretty easy because the two relevant terms in the metric are just -1 or +1. So when I lower the index in components, I get -1 along the t direction, and I still get +v along the r direction. The interesting about this is that I can write down the velocity field as a gradient of a function. Because what this equation means is that the t component here is going to be the gradient with respect to t of that function, which is 1, with the -1 that I've inserted here. And then the r component of this vector is going to be the r component of the gradient of this function, which is -v times -1, which is the v I had here. So we saw last time that when we have a velocity field that happens to be proportional or equal to the gradient of a function, then that means that this congruence is hypersurface orthogonal. So that guarantees that, that we have a vanishing rotation tensor, and it also guarantees that, and that guarantees that we have a hypersurface orthogonal congruence. And that's should be obvious because whenever I'm writing the normal, so whenever the tangent vector field is proportional to a gradient, that means that the normal to the hypersurface described by that equation is going to be aligned with u. So this is normal to hypersurfaces phi equals t minus v over r equal constant. So I have a bunch of hypersurfaces like this with a bunch of constants, and the gradient to this function then is by definition the normal to those hypersurfaces. And what I'm saying here is that the velocity field is aligned with that normal, and that's the statement that my congruence is hypersurface orthogonal. So the congruence is hypersurface orthogonal, and they're orthogonal to those surfaces over here. I'm going to draw them a little bit later when I'm done doing the rest of the calculation I wanted to do. Is that clear? Yeah. Okay. So that's an interesting congruence because we have this property and we have a whole bunch of hypersurfaces that come for free from the construction. Okay. So what I want to do now is to just use this tangent vector field and calculate its gradient. So the tensor B, that was the starting point of our discussion of the relative behavior of geodesics in a congruence, is the gradient field, is the velocity gradient field. So you just do the computation. And if you do the computation, I'll just give you the answer. You find a diagonal tensor that has 0 entries in T and along TT and RR. It has a non-zero entry along theta theta, and then it's equal to that along the phi phi direction. So, sorry?
Should there be double brain derivatives?
Oh, sorry. Yeah, it's the tensor D alpha. Alpha beta, thank you. So B alpha beta. So it's a diagonal tensor, and from the form over here, we recognize that it's also a spherically symmetric tensor, and on top of it all, it's a symmetric tensor. So there's no antisymmetric component to that tensor, and that means that the rotation tensor vanishes. So B alpha beta is the same thing as B beta alpha, and that means that the rotation tensor vanishes in this case. And, well, that goes back to the statement I made up here, that we are dealing with a hypersurface orthogonal congruence. Okay. What I want to do is to decompose that tensor into its irreducible components. And the first step in doing that is to introduce the transverse metric. So we have to introduce the transverse metric to the congruence, that quantity H alpha beta that we talked about before. And in this case, I have to modify the definition because my vector u is not normalized. So that's the only change I have to make to allow for the non-standard normalization. So the transverse metric in this case is still going to be the metric plus something that goes along u, but now I have to make sure that I divide by that in order to make H transverse. So the point is that if I multiply this by u beta, I still get u alpha from the first term, and I will get u alpha from the second term, but now I get u beta multiplying u beta, and I get this back with a -1 because it's negative, and u beta is going to be, so sorry, this is positive, u beta is negative, so you get minus u beta over here, -1 I should say, and that means that we get 0 as we should. So if you don't normalize your vector field, you just adjust the definition of H so that it actually satisfies the usual properties. And with that, everything else follows. So all the other properties of H that we worked out last time will continue to be satisfied. Okay, so if you calculate this, you get something with components all over the place. So I won't display that for you. So that's something, so, that's a good exercise for Maple to do. So you just, plug in the definitions for your velocity field. You plug in a definition for B. You ask GR Tensor to calculate the components of this tensor. You find something very simple. Then you plug that into GR Tensor and you ask it to calculate the components. And you find something which, is really not pretty to look at. So we won't be looking at them. We won't be looking at it. So it's complicated, but of course, it's still something that can be put in to a matrix, and it's going to be a symmetric matrix in those coordinates. So it's not worth staring at it. The shear tensor is also complicated. So what I'm doing here is to decompose B alpha beta in terms of its reducible pieces, and there's no rotation tensor, so I don't put it in. If I want to calculate theta, of course, I have to take the trace of B, so that's why I needed the transverse metric, but of course I don't really need it because this is just equal to the usual trace, which is just equal to the 4-dimensional divergence of that vector field. And when you calculate this, you find something which is actually pretty simple. You get 2v over r. The shear tensor is complicated, but the square of the shear tensor is just a scalar function. so that's actually pretty simple. You'll take my word for it. It's 2/3 v squared over r squared. And the last thing I want to calculate is d theta d lambda, the acceleration associated with the rate of expansion. So let me just do this here. D theta d lambda, I'll just do this calculation in real time so you see how it's done. So it's just the rate of change of the expansion parameter along the congruent, so it's along the vector u. Now, the expansion only depends on r, so the only component to this equation that's going to matter is the radial component. So we get theta differentiated with respect to r times the r component of the velocity vector. The r component of the velocity vector is v. Where was it? It's hidden somewhere. It was v, so it's v times d theta dr, and that's easy to calculate. It's minus dv r squared, so minus 2v r squared. So we get minus 2v squared over r squared for the rate of change of the expansion. Now, according to Raychaudhuri's equation, this should be equal to minus 1/3 theta squared minus the square of the shear tensor. And it would be a disaster if that didn't turn out to be true, but I think it does turn out to be true. So over here, we get theta squared, so we get 4 times over 3 v squared over r squared. So here we got 4/3. Here we get, for the square of the shear tensor, we get 2/3. So we got 4/3 plus 2/3, that's 2. That matches what we, that matches the 2 that we have over here. And the minus sign, of course, is respected as well. So we have a check on that. It all works out. Everything's beautiful. Right. So in agreement with Raychaudhuri's equation, we find that because we're dealing with a congruence of time like geodesics in flat space, we find that there's a deceleration in the rate of expansion. So this quantity here, being in flat space time, is guaranteed to be negative. But that's also true from Raychaudhuri's equation, given that we have a situation where the rotation tensor is 0, and therefore there's no possibility of having a positive term on the right-hand side. I think it is possible to come up with congruences in flat space-time where the rotation tensor would be non-zero, and then basically it has to be, a matching, it has to be true that the positive rotation term would not be overwhelmed by those negative terms over here, and I think that always works out as well. All right? Yep.
If you were to ask me before we go through this, if the shear tensor would be not 0 or 0, I would probably say 0 because you think an expanding shell, it's not, it's just expanding, it's not shearing. So
yep.
Can you explain why we have a non-zero shear tensor?
Why is it shearing?
Yeah.
I wish I could draw a picture that would reveal that very clearly, but I think it's a little bit tricky. What's really happening, and it's not obvious, and you'd have to draw a very careful diagram in order to see this, is just that the radial behavior is a bit different from the angular behavior. So that in fact, as the congress expands, it does something different along the angular directions from what it does in the radial direction. So that in fact, figures get elongated in one or the other direction instead of staying spherical. So it's really not obvious, but it's something that if I were talented enough, I think I could try and draw a diagram that would reveal that. But yeah, it's not obvious. To get no shearing, you would have to have an expansion that's really uniform in all directions, but we're not dealing with that here. So a cosmological expansion would produce no shear. An expansion along the cone does. It's not totally obvious. So not a very good answer, I'm afraid. That's the price for asking too many questions. You don't always get satisfactory answers. Any other questions about this? Okay, so let me come back to those hypersurfaces, and then I'll think about taking the null limit. So I'll just redraw the diagram that I had over on the other side. So that's the x direction, that's the t direction. And I had a few of those wedges that represent my cones with a bunch of dimensions suppressed. So those lines all have a slope larger than unity because they represent word lines that move with a speed, slower than the speed of light. Where are my hypersurfaces? Okay. These guys, the hypersurfaces phi equal constant will be represented on this diagram with straight lines, but with a slope that's larger than unity, smaller. This is larger. I want to draw other slopes, other lines with slopes smaller. So for example, so this is the t equals 0 bundle. This is the t equals 1 bundle. This is the t equals 2 bundle. The phi equals 0 hypersurface is going to start at r equals 0 with t equals 0. So it starts over here, but it goes like that. So I'm going to draw them in dashed line. So this is the phi equals 0 surface. While the phi equals 1 surface would also start at r equals 0 with t equals 1. So this would be the phi equals 1 surface. And, continuing like that, this would be the phi equals 2 surface. So this is a large slope. This is, so the slope is v. And the slope here, the slope is 1 over v. And the slope here is v. It doesn't look like it, but in a space-time diagram, those two curves, those two lines are orthogonal to each other. This and that. This and that, and this and that. So it doesn't look orthogonal on the diagram, and that's the benefit of having a minus sign in the metric. Things look strange in a space-time diagram, but the statement is that in a space-time sense, those hypersurfaces are orthogonal to those geodesics. That's interesting. Well, something that's rarely mentioned, but statement of orthogonality in space-time diagrams is not necessarily the thing you would expect. Where it gets really interesting is when you consider taking a limit where v goes to 0. And I'll come back to that in a moment. I just wanted first to talk about the metric you would get if you restricted your displacements to each hypersurface. So I want to calculate what I call the induced metric on each hypersurface, something that we'll start talking much more maybe this afternoon when we start talking about congruent hypersurfaces. But here I just want to do a little exercise that's going to illustrate something when we take the limit. So on each hypersurface, T is restricted to be V plus R and plus a constant, which means that displacements in T are related to displacements in R by this relation. And if I want to calculate the metric purely on the hypersurface, restricting myself to displacements on the hypersurface, what I need to do is to go back to the flat space-time metric and plug in what dt stands for when we live on the hypersurface. So the induced metric on each hypersurface is obtained by taking the space-time metric and just plugging in this expression for dt and combining it with the rest. And what I'll get, of course, is a perfectly fine three-dimensional metric on my hypersurface. So the line element on the hypersurface is going to be 1 minus v squared, the r squared, plus the rest of it. I should have introduced this approximation, but d omega squared just stands for all this here. Now, apart from the factor in front of dr squared, it looks as if we're dealing with something pretty simple, right? It's a constant coefficient times dr squared, and we get the rest of it. So apart from this constant coefficient over here, it looks like just the flat metric on a three-dimensional surface, on a three-dimensional space. But in fact, the fact that the coefficient here in front is not zero tells us that the intrinsic curvature of that surface is actually non-zero. So that's another little exercise. You can plug this metric into GR tensor, calculate its Riemann tensor, and I'll just display a component here. The only non-vanishing component, I'll write it in this form, so it's r theta phi theta phi theta phi is given by minus v squared divided by 1 minus v squared multiplying r squared. So this is a surface with a three-dimensional metric that has an intrinsic curvature, and in fact, it has a pretty violent curvature singularity at r equals 0. And that's not too surprising because there's a kink over here in the surface, and it's not too surprising that there should be some singularity associated with that. But metrically, and the curvature is certainly very singular at r equals 0. But that's fine. I'm not concerned about that. I'm not concerned about that because we've excluded the axis from our considerations anyway. So this singularity is something that I can live with. Okay. Now I can take the light-like limit, and we're going to see some interesting things happening. So suppose that I take this congruence, but now I let v approach 1. Well, what's going to happen to my cones over here is that they used to be pretty narrow. They're going to open up, right? The slope is going to starting approaching 1. So all of those curves over here will just open up so that each cone will approach a slope of 45 degrees. That's what happens when time-like geodesics go toward being null. Those hypersurfaces, they do the opposite. They were very wide, and now they get narrow until they also approach a slope of 1, right? Because the slope of this is the inverse of the slope of that. If one slope approaches 1, the other slope has to approach 1. So as we crank up v and we let it approach 1, these widen up, approach 45 degrees. These get narrow and approach 45 degrees. And in the limit, they all coincide. Everywhere along the limit, we had this property that those curves were orthogonal to those hypersurfaces. And that property remains true in the limit. But now it's weird because in the limit, this starts to, this coincides with that, this coincides with that, and this coincides with that. And yet we don't lose this statement of orthogonality between the curves and the hypersurfaces. That's where things are so strange and require so much care when you take a light-like limit, is because something that used to be distinguished in a space-time diagram becomes coincident. So in the limit, v tends to 1, we get cones at 45 degrees, and we get hypersurfaces at 45 degrees. So this represents the hypersurface and the null geodesics. The null geodesics are orthogonal to the hypersurfaces. That remains true. But if the null geodesics are lying in the plane, in the hypersurface, they're also tangent to them. So null geodesics are tangent to the hypersurfaces. And I can say both statements, and they're both true. So in the null case, we get a tangent vector field that is null, and a null vector is orthogonal to itself. Therefore, a null vector will be orthogonal to the hypersurfaces, while at the same time it's lying right in the hypersurface. That's the weird thing that happens when you take a limit. Before you take the limit, everything is distinguished, and the tangent vector field is certainly not going to be it's not going to be tangent to the hypersurfaces. It's tangent to the geodesics. But in the limit, everything coincides, and the null geodesics are both tangent and normal to each hypersurface. So that's the that's the benefit of having a Lorentzian metric, and it opens up all sorts of complications that the classic differential geometers of the 19th century never saw coming, and created all sorts of neat things for us relativists. The source of all of this, I just said it, but it's the point that in the null limit, the tangent vector field becomes null, and that limit, let's see, where did I put my tangent vector field? I lost it somewhere. Yeah, so the point, over here, yeah, thank you. So the reason why I didn't normalize my vector field is because I wanted to be able to take that limit easily, right? V goes to 1, there's certainly nothing wrong going on at the level of the tangent vector field. If I tried to normalize it, then my normalization would become singular in that limit, so that's why I didn't do that. But certainly the limit of the vector u is well defined in the null case when v goes to 1, and we get a normalization that's 0 in that case. And that's the statement that a vector can be orthogonal to itself, and that's very weird, but it's true. And that gives rise to the statement, because we still have a vector field that's tangent to all the geodesics, which are here, and we still have a vector field that's related to this, to the hypersurfaces. That's the statement that this is the normal to the hypersurface. This is, and this is then, combine all this together is the statement that you can have a vector that's both tangent and normal to a null hypersurface. So when we consider hypersurfaces more fully, we're going to see that there are all sorts of consequences that need to be understood and dealt with when we consider null hypersurfaces. That's just a little bit of a little bit of a taste, coming to that discussion. But one thing that is also directly relevant for us here is the fact that when I take the limit v goes to 0, something weird happens to my metric. Sorry, when v goes to 1, something really weird happens to the metric. I'm getting a 0 factor in front of dr squared, which means that effectively I'm losing a dimension. In the limit, ds squared becomes r squared d theta squared. So the way to describe this is to say that the metric becomes degenerate. It has now a 0 eigenvalue, while before we didn't have 0 eigenvalues. We only had positive or negative eigenvalues. But more effectively, more usefully for us, what we can say is that the metric becomes effectively two-dimensional. We lose one of our spatial dimensions when we take the light limit. And that's interesting, and that's directly relevant for studying congruences in the null case. We're going to have to deal with that. I mean, it's a very important aspect of the discussion that's coming up next. And that's something we need to think a little bit about. Now, suppose that I look at this hypersurface over here. It's a line at 45 degrees. So let's look at this line over here in the space-time diagram. It's a line at 45 degrees, and we know that on this line, dt squared is equal to dr squared. And that means that on this line, ds squared is equal to 0. So going along that line gives me a 0 displacement in space-time. That's not surprising. That's just a statement that we're moving along in a null direction. So we expected that, but we get more than this, because we also get the same property over here. Because of this, we're losing one dimension. We start from 4 dimensions in space-time. We decide that we're going to be traveling along a null line, and we lose one dimension. And that's what happened here. But because that happens also on this line, we're in fact losing 2 dimensions. And what's left over essentially is an effectively 2-dimensional space that now is transverse to those 2 null directions. So we have 2 null directions. Along which ds squared is equal to 0. And we got a 2D transverse space where ds squared is not 0. And on the diagram, that 2D, that 2D transverse space is, well, I've suppressed those dimensions, right? But if I were to restore one of them, that 2D dimension would be the one that goes off in this direction, away from the board or in the other direction. So, and if I restore 4 dimensions, I can't draw that. But each one of those points over here and everywhere really represents a 2-dimensional subspace, and it's in that subspace, that transverse subspace, that we get our non-zero ds squared, which is the one that we find here. So the null case is weird because of the fact that we're basically down 2 dimensions. And instead of dealing with a 3-dimensional transverse space the way we were dealing before in the time-like case, the transverse space was 3-dimensional, and the expansion parameter along the congruence was measuring the fractal rate of change of volumes, cross-sectional volumes in that 3-dimensional space. Here we've lost an additional dimension, And what we're going to be dealing with here is a two-dimensional transverse space, and instead of calculating fractional rate of change of volumes, they're going to be now fractional rate of changes of areas, cross-sectional areas in that two-dimensional transverse space along the congruence. So the null case is very subtle. The mathematics are very similar, but the ideas behind them are certainly much more subtle. So that's what I want to do next. I'm going to move away from that and attack the null case directly now. Any questions about this before we move on? Yep. Yep.
How would you do the thing you did with normalization up there? H alpha beta equals G alpha beta plus, so that's infinity.
Yeah, so that breaks down in the null case. So part of what we're going to have to address is, how do we adapt this in the case of null? So yeah, so that thing here, because of this degenerate property of the metric, this just goes away, and that has a singular limit, in fact, when you take the null case. So we're going to have to think very carefully about how to adapt this to the null situation. Yeah, so that's my next job, basically. Other questions? Okay, let's go into that. Okay. So we're going to do it all again, but now with null geodesics. The good news is that the starting point is exactly the same. So all the setup that we did when we started to talk about geodesic deviation, all of this can be imported to the null case. There's nothing that needs to be changed in the null case. It's just that along the way we're going to have to basically face up to the fact that in the null case our vector is normal to itself, orthogonal to itself, and we're going to have to just build this in explicitly. So now we still have a congruence, so we still have a bunch of geodesics all over the place, but now the distinction is that all of those are null. So we still have a full congruence of null geodesics. It has a tangent vector field, so we still do the same thing, right? So there's a tangent vector field. Now instead of calling it U, I'll call it K, just to distinguish the notation. We pick a reference null geodesic, and then we do the usual construction with the cross curves and all of this, and we end up with this notion of a deviation vector. So none of this changes. All of that, has a null limit that's completely straightforward. All the relations that we worked out between all of these things apply. So I'm still going to so the tangent vector field is going to be null. So K is the tangent vector field. Now it's null, so it's not normalized to -1 the way we used to do it before. I'm going to assume an affine parameterization. So my null vector field satisfies the geodesic equation in the usual form. We still have the Lie derivative equation that continues to apply in this case. So the derivative of the tangent vector field in the direction of xi is the same thing as the derivative of xi in the direction of k. So that's just the Lie derivative property that, again, just imports here just as well, and that follows just from the construction in terms of the cross curves that we saw before. And another property that we can impose that we had in the time-like case is the fact that we can always remove a component of xi along k and choose xi to be orthogonal to k. So that's a condition that we imposed before. That's a condition we can still impose. The problem here is that it really doesn't do very much, because if xi had a component along k, this wouldn't kill it, right? So if xi has a term, if xi is ak plus something else, well, the ak multiplying this would just give 0 because of that equation. So that equation, even though it looks like it should kill off a component of xi along k, it actually doesn't. And we're going to have to work a little harder in order to remove that component along k that we don't want. So that's going to be part of the story, and it's all the wonderful aspects of having vectors orthogonal to themselves. So this equation doesn't kill a component of k, of xi along k. So we're going to have to play a little bit harder for that. Okay. The first thing that I did when we were working through the time-like case was to define a transverse metric for the congruence, because ultimately what we want to know is, having picked our reference null geodesic in the congruence, we want to work out what the transverse behavior of the neighboring geodesics, what that's going to be. So we want to work out the transverse behavior of neighboring geodesics, and a tool in order to achieve this in a time-like case was to define the transverse metric, decompose the metric into a longitudinal piece and a transverse piece. So we have to do that now, and that's where it gets tricky. Well, in the time-like case, it was easy. In the time-like case, we just said it's got to be this. And that had the property of being orthogonal to u. So let's try that was a plus. Let's try that. Is it orthogonal to k? Yes, no? I see one no. That's right. If I multiply this with k, I get k back from the metric, but I get 0 from the second term. So that doesn't work. It doesn't work for the reasons we were talking about over here. It doesn't work because basically I have to lose one dimension. My transverse metric has to be two-dimensional in the null case, and the limit of that quantity, the limit of the transverse metric that we were given there from the time-like case, is singular. And that's something that we saw previously. If I didn't normalize my vector field and took the limit, well, we would find that that limit in the null case is singular, so it just doesn't work to try to adapt the time-like definition to the null case. It just doesn't work like that. Well, we can take a hint from this diagram to sort of identify what needs to be done. In order to isolate out the two-dimensional transverse space, I should exclude this point because it's not, it's not part of the congruence. But what we're trying to do here is to single out the two dimensions that live at that point over here, the ones that are suppressed. And in order to single those out from the 4 space-time dimensions, I basically have to remove this null direction and that null direction. So what we're trying to do is to take the 4-dimensional metric, we remove two null directions, and what's left over are the two directions that are really the transverse directions that were falling out from this construction. Yep.
I don't really understand what you mean, because those two directions only exist at the central axis. If you move along the surface and to the right, say, then that direction pointing to the left, can you do that?
It's right here.
Is that still on the surface, on the hypersurface?
No, it's not on a hypersurface, but it's still a null direction, right?
Yes.
So I have one null direction that's given by the congruence. I have a second null direction that's also there, right? And what I want to do is to remove this null direction and that null direction to single out those two over here.
Okay.
That's what I'm trying to do. So basically, I'm using this. So I'm using this as a, I'm using this discussion that I had before as a motivation for looking for something different from this, because I have to boil it down to something two-dimensional. And here, I think we understand that to get something two-dimensional in this transverse space over here, we have to kill off this direction. We have to kill off that direction. And we kill off the null directions because along both directions, ds squared is equal to 0. So the only place that we pick up a non-zero ds squared is along those two transverse directions. So that's what I'm trying to do here. Right? So in flat space, so this doesn't work. In flat space, what we would try to do is to say, well, here's my t explained again. We would pick a point in the congruence, and we would identify this as the null direction of the congruence. And we will want to remove this. We would pick another null direction, which I'll call an auxiliary null direction. We would kill that one, and then what would be left over is this two-dimensional subspace. And that's the one we want. That's going to be the two-dimensional transverse space that we expect will be the proper thing to do when we deal with the light-like limit. Right? So how do we do that? Well, this one is given to us. We have a null direction already singled out from the congruence. All we have to do is to pick another one. And if we pick another one, then we're fine. Everything else follows. So we're given this one. We're going to select this one. And then we're going to remove both. And then we're going to be left over with that two-dimensional transverse space. That's what we need to do. So we need an H alpha beta that's going to do that for us. Okay? So you can read the discussion in the book. I give you a slightly different take on all of this. But let me just write it out, and then I'll explain what it is. I'll explain that it works. So we're given k alpha beta. We're going to select, we're going to pick a new null vector and alpha that's going to be our auxiliary null direction. Of course, I have to pick a different null direction. If I were to pick the same again, that wouldn't achieve anything. N alpha is going to be a null vector, so it's going to have the usual null property. And then I can pick its normalization arbitrarily because it's a null vector. I'm going to assume, I'm going to postulate that its inner product with k is -1. It's minus because we have two future pointing vectors, and the inner product between two future pointing vectors, whether they're timelike or null, always give a negative number. And I picked that number to be 1. That's just reflecting a choice of normalization for n. And then the claim is that the induced metric that I want is this one. I'll try to motivate that in just a second, but let's first check that it works. It has to be orthogonal to k. So let's check. If I multiply on the right with k, it would work also on the left because this is symmetric. I get k back from the metric. From this guy, I get k back, but I get n multiplying k, and that's a -1 by this requirement over here. And then the last term, I get k multiplying k, I get 0 from that. And therefore, I get 0. So h is transverse to k, and I needed that. In fact, I get a little bit more than that. I also get that h is transverse to n. And I also need that because I really want to have a two-dimensional transverse space, because I want to kill both the direction along k and the direction along n. And that we can verify as well. So if I multiply on the right by n, I get n back from the metric. This gives me 0. And this gives me n back with a -1. So sure enough, I get 0. So at least it looks as if we're doing the right thing. I mean, we're getting something that seems to have sensible properties. But it's coming out of nowhere, so I'll try to motivate that, relative to the discussion we had before. A few of the properties that are worth noting. So this again acts as a projection operator, and if you project twice, it's the same thing as projecting once. So a property that this has is that one action of h combined with the second action of h is like a single action of h. So that's something you can check just from the definition. And another thing that we can check is that the trace of h is 2. And that follows because if you take the trace of h, you get 4 from the metric, you get -1 from here, and you get another -1 from there. And that gives you 2. So in the time-like case, we were dealing with a three-dimensional subspace, transverse space, and the trace of h in that case was 3. And now, appropriately, it's 2. So let me motivate that just so that you see where it's coming from. So let's do flat space again. So the congruence that we were talking about before in the light-like limit is the one that had this tangent vector field. So those were the curves that in the tx plane were moving to the right. So the transverse space we're trying to construct here is going to be orthogonal to this line. But we know that we also have to kill off the other null direction. All those lines over here, we have to remove them as well. And in order to do that, well, we just need to kill off the, we just need to come up with the vector that points in that direction and normalize it properly. So the n vector is going to be proportional to, there's going to be a normalization constant in front, c, but it's going to be pointing in the opposite direction. Right? And all we have to do now is to figure out the normalization. So we just do the calculation, g alpha beta, k alpha, n beta is going to be minus 1 multiplying 1 times C. And then it's going to be plus, so C is going to multiply everything. So we get minus 1 multiplying this times that, so we get the minus 1 here. And we get this times that, so we get another minus 1 from the R component of the metric. So we get minus 2C, and that has to be equal to minus 1. So that means that C has to be equal to 1/2. So N alpha is 1/2, 1 minus 1, 0, and 0. When you take this and that and insert it into here, that's a very simple calculation. You find that the transverse metric is going to have a 0 entry along T and R, and it's going to be the usual thing along theta and phi. And that's the two-dimensional transverse space we were looking for. Right? So, however you look at this, it sort of makes sense. So the null case introduces this additional subtlety that, that the transverse space becomes two-dimensional. We need to be able to identify this two-dimensional subspace, and it's not enough to have, identified just one null direction. We have to identify another null direction in order to properly remove them and isolate out the two-dimensional subspace that is, left over after you remove this line and that line from the space-time. This achieves that. And that's the tool we need in order to proceed and derive the rest of it. Is that becoming clear? Yep.
This choice of metric, is it unique?
I was going to say a few things about that in a moment. Any other questions before we get to this? It's not unique. And N is not unique. And the way to see this is that I'm picking out a vector, but I only have two conditions that I wish to impose on it. And clearly, it's under constraint, and there are lots of ways I can do that. And for each choice, I'll get a different transverse metric. So it's not unique, but that's fine. We're going to live with that. Yep.
Can I also add to it any product of vectors that are thought both and K?
Add other vectors to that?
Add Z alpha to beta, where Z is orthogonal to N and K.
But then you would start killing off some of the directions in the transverse space. Yeah. And that would be killing too much, removing too much. Now, geometrically, what does it mean? So why is it that N is not unique? Well, here, here it was deceptive because I was doing everything in the plane, right? And it looks as if there's only one other null direction. But if you restore a dimension, if you restore, the rotation along T, for example, I have a whole null cone that I can go around when I want to pick a null direction. So all those rotations that I can do, I don't know if you can visualize this. I'm going to try to draw it. So I have a whole null cone over here. And instead of picking this direction, I could have picked this direction or that direction, not this one, or that direction, or any direction along the cone. So I have the freedom to rotate. And N basically can be any one of those null directions that I'm picking out. So it's highly non-unique, and it's unique for that reason, that I have all this, freedom to perform rotations along the cone. So that can seem strange. So the construction is not unique, but that's fine. In practice, we just pick one null direction, your favorite one, and you just work with it. And of course, some of what you do will depend on that choice, but a lot of what you do turns out, and I'll come to that a little bit later, a lot of what you do, in fact, doesn't depend on that choice. So this is not unique because N is not unique. But it turns out that many things that we care about, like the expansion and other things, turn out to be well, the expansion turns out to be unique, and there's some uniqueness aspects to other things that are not, plagued by the non-uniqueness of the vector n itself. And that's something I'll say more about in a few minutes. You had a question?
Maybe you already answered this, but, well, if you can choose n to be any vector along that cone, then shouldn't any vector along that cone be orthogonal to h?
No. Once you've picked n, then h will be orthogonal to only n and k. If you pick a different n, then the different h will be orthogonal to that n and h. So you can adapt the definition, but once you've made the selection, then h will only be orthogonal to those two vectors. Yeah. Any other questions? So it gets some, it requires some getting used to. And in fact, it's a fact of life in GR that whenever you deal with null, the null case, either you're talking, if you're talking about congruences or if you're talking about hypersurfaces, these null issues and, that all originate from the fact that vectors are orthogonal to themselves in a null case. They all come to haunt you, and you have to think very carefully about these things. So, if it looks a little bit mysterious at this stage, don't worry, you'll get used to it, and at some point you'll teach a course and you'll have to do your best to explain it to other people, but it's always a bit of a, of an unusual thing. Okay, so I'll just spend the next 10 minutes just going back to what we had learned before and just adapting it to the null case. So because we start from exactly the same point, this construction up here, a lot of what we did in the timeline case just takes over directly. So carries over directly. We don't need to change anything for a lot of it. So, so a lot of that stuff we don't have to do again. So this equation, for example, up here is the starting point, right? So we define a gradient velocity field, but now it's defined in terms of the null vector. And we still have that Lie derivative equation, and the thing that we want to, of course, get to is the behavior of neighboring geodesics. Once you've selected a reference geodesic, you want to know how neighboring geodesics will behave. So that equation is going to be the starting point of that. And a lot of things that come out of this just carry over unchanged. So it all comes from that. But there are certainly some subtleties, as you're well aware by now. One thing that we have to work a little bit more on is the fact that this equation here doesn't do very much for us. So what we would like to do is to select a deviation vector between neighboring geodesics that's going to be purely transverse, that will have no component along k, and for that matter, no component along n. Before it was all taken, it was all built in, right? So the condition CU equals 0 meant that the deviation vector automatically was pointing in the orthogonal directions, the transverse directions. In a timeline case, we never needed to think about it. But here, we would like to turn that in, turn this into something a bit more useful. And in fact, we would like to project the deviation vector into the transverse subspace and only deal with those components that live in a transverse subspace. So the first requirement is to project C into the transverse subspace in order to do what we really want to do, and is to describe the transverse behavior of neighboring geodesics. So everything that's projected in the transverse subspace, I'm going to indicate with a tilde. And the tool to do that, of course, is going to be the projection operator. That's what it's good for. You take h, you multiply h by your vector, and you kill off all the components along n and k, and you're left over with only the transverse components. So xi alpha with a tilde on top is by definition the transverse projection operator acting on the original xi. And by doing that, there's no bar here. By doing that, we kill off the components along k and the components along u. So that's going to be the proper starting point. And what we're going to want to do is to work out an evolution equation for this projected guy. So more explicitly, I can just plug in the definition for h that I buried somewhere. I get the metric, which in this positioning of the indices is just the Kronecker delta. I get k alpha n mu. I get n alpha k mu. And I get xi. If I do the multiplication, I get xi back. Then I get something along k. And again, then I get nothing because xi times k was already imposed to be 0. So the point is that this has something along k and possibly something along n. This kills off, so this had something along k, this kills it off, and there was nothing along n because this is already 0. So the point is that after adding this guy to this, I get something that is orthogonal to both k and n. That's what I should indicate. So this multiplication here guarantees that xi alpha is orthogonal to both k and n. What we just found is that this condition up here was in fact not removing a component along k, it was removing a component along n. If we didn't impose this condition, we would have a component along n, we have this component along k, and adding these extra pieces basically remove them from xi. So xi tilde is now properly transverse. It's got everything in it that we want it to have. All right. Well, now that I have the deviation vector, the one that I really want, well, what I want to calculate is its evolution along the congruence. So that's what we really want to do with that. So this is the transverse deviation vector. So let me push this up. And the rate of change of that transverse deviation vector is the thing that I really want on the left-hand side of that equation. So we want to calculate the rate of change of the transverse deviation vector. And by that I mean take the transverse deviation vector and calculate its rate of change along k. And, well, we just do the calculation. We'd get xi differentiated along k. Then we get the derivative of that scalar along k. And then we get the derivative of k along k. So the last term is 0, because this satisfies the geodesic equation, as we have to work out. This is going to be given by the derivative of the n vector in the direction of k, and this multiplies xi mu. and this multiplies the k alpha that's left over. And then we have the derivative of the new vector, xi vector, in the direction of k. So what do we have? This is b multiplying xi. And then what do we have? We have let me back up for a sec. Oh, okay. Yeah, this is another b. So this is, let me write this term here. So we get m mu, we get b mu beta k beta, xi beta, and we get k alpha multiplying that. And then we get this guy over here, and we get n mu differentiated k beta, and then we get xi mu, and we get k alpha. So it's a little bit messy, but it's going to simplify. Right. I'm sorry, I'm not following my notes here, so I'm following a different route. I got myself lost, I think. Okay, no, I think I could recover from that, but I think we're running out of time, so I'll just pick it up from here. I'll restart that this afternoon, so I can clean this up and do it a little bit differently, so I can follow myself instead of trying to recover from here. Sorry about that, but anyway, it's not as bad as it seems. So, okay, any questions before we break? Okay, so we'll just pick this up again in the afternoon.